The first sentence here says it's possible to burn ammonia in the presence of a platinum catalyst and a controlled amount of oxygen to form nitrogen gas in the steam. So let's see this reaction first. Here's an experiment done by Philip Evans. He's bubbling oxygen through an ammonia solution, and the ammonia and oxygen mixture is bubbling out, and he's igniting it with a platinum wire, which is a catalyst for this reaction. And those flashes of light are the ammonia and oxygen burning into nitrogen and water vapor. Ammonia is used as a refrigerant, so you can set it up and use it to chill things. This is the inside of a yogurt plant where they're chilling down some yogurt. A pipe breaks, and as the ammonia fills up the room, eventually there's enough of it and there's a source of ignition and the plant explodes. So that's the combustion of ammonia, catastrophically. Well, indeed, you can see that ammonia does burn. And let's find out quantitatively exactly how much energy we get when it changes from ammonia and oxygen to nitrogen and steam. We're going to use Hess's law for this, and Hess's law is pretty straightforward. You figure out the enthalpy of your products and you compare it to your reactants, and the difference between the two will be the enthalpy change in your reaction. Now, what we start with are the enthalpy of formations. Now, that indicates that we must have a table that tells us how much energy we get when we make these substances from their elements. And here we've got a table, and on the AP questions, they'll end up having a table for you. And as you can see, they've got three materials here. They've got steam, water, and ammonia, but you'll notice that your reactants have got oxygen and nitrogen in them, and they're not in this table. And there's a good reason for that, because enthalpy of formation tables values are defined as what the enthalpy change is when you make a substance from its elements. Well, when you make steam from hydrogen and oxygen, it's an exothermic reaction, and you get 242 kilojoules of kinetic energy released. You drop that much potential energy. But oxygen, if you make oxygen from oxygen, nothing happens. So by definition, any element has an enthalpy formation of 0. In fact, you like to see elements in your reactions because you're not going to have to deal with them because they're zeros. And if you're adding and subtracting, it's not going to be anything at all. So I'm going to get my line out here, my pen, and I'm going to just cross out the oxygen because I know it's not going to be involved in this reaction, and I'm not going to have to worry about it. And I'm going to cross out the nitrogen. So that makes this reaction in terms of calculation for enthalpy of formations simpler. All I've got to do is worry about the steam that's made and the ammonia that is reacted. Well, let's look here. We've got our ammonia, and the reaction says that this is one of the reactants, that we're going to need 4 moles of ammonia, because this is going to be per mole of reaction. That's how AP deals with these enthalpy of formation tables. So we have to find out the total enthalpy of 4 moles of ammonia. So let me pull up my calculator and clear what's been there. And so I'm going to take my ammonia, which is let me bring this up a bit so I can see the entire keyboard, a negative 46 kilojoules, and that is for 1 mole. So I've got 4 moles, so I just multiply that by 4, and I get my value, a total of a negative 184 kilojoules per mole if I'm going to end up making ammonia. Now, that, I'll save, and there it is, negative 184 kilojoules. Now, the other thing I've got in my reaction here is my water, and I'll pull up my calculator and type in what I need here. So now I said water. I should have said steam. Phase is very important. Notice they have liquid water. When you make liquid water from hydrogen and oxygen, you're condensing the steam, so you get even more energy. If you're just producing steam from hydrogen and oxygen, it's a negative 284. Now we'll put our negative sign in there. Enthalpy reactions, you got to be very, very careful with the sign. Negative 242, and that's for 1 mole. This is for 6, so just the multiplication of 6, and then we get a negative 1452 kilojoules of energy, and I'll put that in there. So we start off with our reactants having a total of negative 184 kilojoules. Now, be very careful, because one of the problems with Hess's law is that you've got products minus reactants. The second thing after the first. That's what changes are always about. And you see the reaction, you say, okay, I'll put it down here. Don't. That's a very common error. You put that negative 184, and I'd put it in parentheses, and because we have a subtraction, we want to have the difference between these two energies, put that minus on there. The math in these things is relatively easy. We're not dealing with quadratic equations or anything else, but you've got to be very, very, very careful with your additions and subtractions and your signs naturally. Now, we've got our enthalpy of formation of our products, and again, we didn't have to worry about the nitrogen because that's an element, and we have a nice simple negative 1452 kilojoules minus a negative 184. We probably only have two significant digits on this negative 184. Oh, excuse me, 3 significant digits on this and 2 on here, but let's carry this out to the nearest whole kilojoule and do that subtraction. I'll get my calculator out, and I've got my answer, my negative 1452, so I'm just going to show my answer. And basically I can just do a subtract that last answer and subtract, and I'll use that negative 184 and get our final answer, negative 1268. Probably, I would say that our honest answer would be negative 1270 kilojoules, but it'll be acceptable in this. And I'll just take this and let's see if I can move it around and just move this into my answer. Now, again, our units are important. When this says per mole, it doesn't mean per 1 mole. It means per mole of the coefficients. If you take 4 moles of ammonia, 3 moles of oxygen, and make 2 moles of nitrogen and 6 moles of steam, the change in enthalpy is going to be a negative 1286. What happens is that our potential energy drops that amount. In fact, let me pull this diagram up here because this is an important one. We start with reactants, ammonia and oxygen, and they have a certain amount of stored energy in them. And they have their bonds, the nitrogens and the hydrogens, single covalent bonds, or oxygen with a double bond. And they have this stored enthalpy. We're not sure what the total value is, but we know what it is relative to the enthalpy of formation. And then they're converted. The bonds are rearranged. They're changed into nitrogen with triple bonds, and our oxygen-hydrogen bond, which is pretty strong because oxygen and hydrogen atoms are pretty small, so that those bonds are short ones. So we have made stronger bonds for our products. And when that happens, kinetic energy is released. That's these flames that come out of here. The heat that goes out of the system that blew up that yogurt factory and has our products. And our results, our nitrogen and steam, have less stored energy in them because that energy was released. So it's important to remember that. If you have any combustion reaction, your final answer has to be exothermic. And negative means that you're losing potential energy. Well, there's our problem. It makes sense. We get a value that is exothermic. The numbers look good. And for a combustion reaction, having something in terms of thousands of kilojoules is a pretty typical answer. So now we have a nice example of Hess's law.